All right. Now that we have understood about quantum numbers, all the four quantum numbers, let us take up a little bit of questions so that we understand it much better, and then let us go to the principles which are followed when we have to describe the electronic configuration of atoms, of electrons in an atom with the help of all three numbers. Okay, so let's do some sample questions first. So if they say n is equal to 2, L is equal to 1. What is that meaning? It is n is equal to 2, you will write like this. L is equal to 1. L tells you the subshell, 1 is P subshell. So it is just telling you that it is 2P subshell. You can just write it as 2P, but I'm just telling you. And if they say n is equal to 3 and L is equal to 2, it means that it is 3D subshell. Third floor, D subshell, right? And D subshell has 5D orbitals. We understood that, correct? Now, if they ask you, like for 3D, if I have to write what are all the quantum numbers for electrons in the 3D orbital. So what is n here? N is 3, L will be 2, and M here, because it is a 3D subshell, it will have 5 3D orbitals. So what will be the value of M? This will be the value of M. So in case they ask you a question like they give you the subshell, write all the numbers. This is what you will write. Okay. Now, which orbitals are not possible, they can ask you. So if they say 1p, this is not possible because p starts with the second subshell, second shell, sorry. 2s is fine, 3s is fine, 3p is fine. If they give you 3f, this is also not possible. Okay, because f starts from the fourth. So initially s, second s and p, spd, and then spdf. Alright, so if they give you, yes, let us say which quantum numbers are not possible. Okay, so they might ask you these type of questions. L is equal to 0, M is equal to 0, MS or S is half. Now this is fine, but this is also fine. This is also fine because I can have this. But this is not valid. N starts with 1, so that means it is not possible. Okay, so let us say one more. N is equal to 1, L is 0, M is 0, and MS or S is minus half. This is allowed. For N value 1, L will be 0 to 1, which is 0. So this is also fine. M is also 0. This is also 0. Don't just check if this is valid. For this, is this correct? That is all. That also you need to check. If I have N is equal to 1, I cannot have L is equal to 1. This itself is not valid. But if I say N is equal to 2, L is 1 is valid. Okay, so you'll have to check from the principal quantum number onwards. So first check if this is valid. For that, correspondingly, if is L valid, for the given L is M valid. That's how you need to check. See, if I say N is equal to 2, L will be 0 and 1, correct? So L is 1 is fine. And what will be the M values? Minus 1, 0 and 1. So these are the valid ones. So if at all they give you 1 is minus 2, for this combination it is not valid. L being 2 is valid. Okay, so that is how it is. And the one more set of questions will be how many electrons can have these numbers. Okay, so number of electrons having the following numbers. How many number of electrons? Which has got N is equal to 4 and MS is equal to half. They can give you any combination. See, N is equal to 4. That means it's a fourth shell. What is the total number of electrons in the fourth shell? It is 2 into 4 square. It is 2 into 4 square, which is 32. So you have 32 electrons, but that is the number of electrons with N is equal to 4. But there is another condition. Out of that 32 electrons, 16 will have plus half, 16 will have minus half. That means this is the answer. There are 16 electrons with the number N is equal to 4 and MS is equal to minus half. One more. How many electrons can have N is equal to 3 and L is equal to 0? They can give you 1, they can give you 2. It always starts from the principal. In the order you should go. N is equal to 3. How many electrons? So 9 to the 18 electrons. Correct? Now, see, N is equal to 3. Visualize this. You have this. This is 3. correct? So this is your first shell, second, this is first shell, second shell and third shell. N is equal to 3 is here, and you know there are this thing. L is equal to 0 will be only 2 electrons then, correct? So only 2 electrons. If you feel it like this, it's easier. Otherwise, what you need to do is N is equal to 3 will have how many possibilities? If you cannot visualize this, see, because there is only 1, it can hold 2 electrons, right? So N is equal to 3 means L value will be 0 to 2. So it can be 0, 1 and 2. This is the value of subshell. For L is equal to 0, M is also 0. That means it's a s orbital, and how many electrons will be in the s orbital? 2 electrons. Any orbital will hold you only 2 electrons. Alright? Yes. Suppose if they give you something like this, 3dz square. How many electrons can have this? Correct? Now, dz square in general will have, it is in the m orbital, d subshell, right? Third shell, d subshell, dz is the name of the orbital. So what will be the number of electrons in the dz? Each orbital will have 2 electrons. So here also it will be having 2 electrons. Okay, so they can ask you these kind of questions. Alright. Now that we have understood, we will try to understand all the rules how electrons are filled. How does the filling of electron takes place in various orbitals? Now to understand that, you need to follow certain rules. Right, so see, in your lower grades, if I say carbon, how you used to write the configuration? 6 is 2 and 4. What it means? In the K shell there are 2 electrons, outermost here there are 2 electrons, and here there is to be 4 electrons in the L shell. Now you are going to write it not just with respect to shells. We are going to arrange the arrangement, or what I should say, the filling of electrons in the various orbits, not just orbits. We are going into the subshells, how electrons are arranged inside the subshell, and how they are arranged inside the given subshell, how they are arranged inside an orbital. So we are going deeper and deeper now. Earlier we just used to talk that this person is residing in the first floor, second floor, third floor. In the first floor there are 2 people, in the second floor there are 4 people. Now we are understanding that these 2 people who are there in the first floor, what is their flat number, what is their room number. Okay, so that level we are going to understand. So we are going to write electronic configuration in a more refined way, and to write that you need to know of a little bit of principles. And the first principle here is going to be the Aufbau principle. Okay, so this is your Aufbau principle. Aufbau, see, generally when we say some principle, it's the name of a people, but here it is not a name, it's a German word which means to build up, to increase or to build. Okay, so that means what it tells you, this principle tells you that the electrons are to be filled in the orbital in the increasing order of their energies. Increasing order of energy in the orbital. Alright. So whichever orbitals also have got definite amount of energy. Whichever orbital has got lower energy, that should be filled first. And how it is like, the orbital with the least energy will be filled first, and then it goes higher and higher. Okay. Now how do we know which orbital has got least energy? For that there is a rule which was given by Bohr and Bury, which is called as Bohr-Bury rule. What it says is, it is also called as the n+1 rule. Now this rule tells you that if I tell you 5d orbital and 6p orbital, which is having greater energy, you cannot say that, right? Just like that. So you should know which is having lower energy and which is having higher energy. So that rule, which rule gives you that? Bohr-Bury rule. What it tells is, minimum L, if the sum is minimum, if this n plus L it is, sorry, not n+1, n plus L. If this value, if this sum is minimum, that will have the minimum energy. That orbital will have the minimum energy. Okay, like for example, If I say 1s, 2s, 2p, 3s. Let us calculate n plus 1 for everything. We are going to calculate n plus n. N is 1, L is 0 for s, so it is 1. N is 2, S is 0, so it is 2. N is 2, for P, L is 1, so it is 3. N is 3 and this is 0, so it is also 3. Now look at that. That means electron comes here first. After 2 electrons are filled, the next electron comes to the 2s. After they are filled, they go to the 2p. But 2p and 3s both have the same number. The sum being minimum has got the least energy. Right? So then, if that is the case, n decides the consider minimum n. Okay, so if at all n plus L is same in two cases, in whichever cases the n is minimum, that will be the minimum energy. So in this case, the sum is same, but n is minimum here, so it goes in this order. Okay, so this is about the roles variable. So if I know, I can do it for anything. Let's say for 5p and 3d, for example. Okay, so 5p, what is it? 5 plus 1, which is 6. For 3d, 3 plus, what is L value? 0, 1, 2, so it is 5. That means this get filled first. Okay, now every time we cannot remember this, so there is a trick to remember this. Alright, so you can write it in terms of a block like this. This is the trick, because every time you cannot calculate. Okay, so there is a diagram, so you write it in the increasing order of their shells. So 1s, in the first shell there is only 1s orbital. Here you have 2s and 2p. If you're talking about subshells, we are not getting into the orbital level. This is subshells. Okay, I'll talk about it. This is 3s, 3p and 3d, and then you have 4s, 4p, 4d, and there is f also, 5s, 5p, 5d and 5f, 6s, 6p, 6d, 6f and 7s, 7p. That's all. You can write here, but this much is enough. Now what you do, you put an arrow like this from top right to left bottom like this. Okay, it should be, this is the simplest way. You can easily draw this diagram. And then you will start from here. So that means first is 1s, least energy subshell is 1s, and after that it is 2s, and after that, look at that, 1s, 2s, then it starts from here. It is 2p, and then it is 3s. After 3s, it is, where is it? The next line, it is here. It is 3p, after 3p, 4s, okay, and after that it is 3d, 4p, and so on. Okay, so 4p, 5s, 4d, 5p, 6s, 4f, 5d, 6p, 7s, 5f, 6d, 7p, 6f, and so on. So this is the order. Okay, so unless this is filled, this will not get filled, and we have written subshells. Alright, so this is about the Aufbau's principle. Now there is a term which is called as degenerate orbitals. This is very, very important. What are degenerate orbitals? Orbitals with the same amount of energy. Orbitals with the same energy are called as d orbital. Let us go back to this diagram. So this was your 1s, and here you had 2s and 2p. This was the subshell. 1s had only one s orbital, so we cannot talk about degenerate here. But if you are talking about 2p subshell, it had got 3 orbitals, right? P is L is equal to 1, M will be minus 1 to plus 1. So you had px, py and pc. All of them will have the same energy, and hence they are called as degenerate orbitals. So give an example means you can write px, py, pc. You can write 2pxy, 2py, and 2pc, 3px, 3py, 3pc. Similarly, if you are going next, you have d orbital, d subshell, which has got 5 d orbitals. All the 5 are degenerate. So within a subshell, all the orbitals are degenerate. Please remember that. Okay, so if you are talking about 4d subshell, all the orbitals, d has 5 orbitals, all the 5 are degenerate. Alright, yes. So this is the first principle. Now And this is the order you need to remember. You can just draw it over a period of time, you'll get it naturally. Okay, so yes. When I do the configuration, I will write it for you, but you can keep this handy and look at it whenever you want to. So Aufbau's principle is done. Now let's talk about Pauli's exclusion principle. What it means that, what is the meaning of exclusive? Something which is unique. It tells that there are no two electrons can have all the same 4 quantum numbers. That means every electron is unique. There are no two electrons within an atom that can have the same number of quantum numbers. Same 4. Even if 3 are same, the 4th one will be different. Alright. So, now if you are writing it, you don't have to write it in the shell level. We write it like this. So, first is 1s. Correct. And then it is 2s. And then it is 2p, which has got 3 orbitals. Correct. Now, if you are talking about an electron here, we write it this way. Each orbital is like a double, bedroom with double bed where 2 people can stay. Here 2 electrons will be residing. So this is the way we denote. This means it's clockwise and the other one is anti-clockwise. So the 2 electrons are unique, that even if they are in the same floor, same flat and same room, they are spinning differently. So that way they are unique. Alright, so now if I talk about an electron here and an electron here, look at that. They both are in the same spin. That means S may be half. But L value is different. L is 0, L is 1. N is 1, N is 2. Correct? So that way there are no 2 electrons which can have all the 4 quantum numbers same. And even if you are talking about 2 electrons here, both the electrons have N is equal to 1, L is equal to 0, M is 0. But their spin will be different. One is positive, one is negative half. Okay, so that is what it says. Alright, yes. Next rule is about Hund's rule of maximum multiplicity. What is this rule telling you? It is just like swings in a park. Now imagine there are 3 swings in a park and each swing can accommodate 2 people. So if you have 3 swings in a park, 1, 2 and 3, the first child comes, he will occupy this swing. And if there's another child coming, he will not like to sit here. He would like to first sit here. And then the third child comes, he can sit here. Now if there is a 4th child, he doesn't have any option. He has to pair with the first or the second or the third child. Correct? And the Hund's rule of maximum multiplicity is something like that. It tells you that pairing won't happen. Pairing won't happen. Now when you're saying pairing, we are talking pairing in a degenerate orbital. Till every orbital is singly occupied. What is the meaning of this? I will tell you. Okay. Now consider this is your 1s, this is your 2s, this is 2p orbital. Okay. Now how do we fill the electrons? It's in the increasing order of Pauli's principle. 1s has the lowest energy, so it will get completely filled, 2 electrons. The next electron will go to 2s because it's the next, it has the next amount of energy. So it will come here. Now 4 electrons are done. The 5th electron will go here. The 6th will not pair. The 6th will go here. 7th will go here. 8th, 9th and 10th. This is how it happens. So in case of a degenerate orbitals which are within the same subshell wherein the energies are same, pairing will not happen till each one is singly occupied. Okay, and the reason why we have this is because arrangement which has got higher multiplicity is, now that is what the name tells. There is a concept of multiplicity. What is this multiplicity? Now to remember, you can remember this statement, but in case they ask you multiplicity, multiplicity is calculated by 2s plus 1, where s is the sum of the spin. Okay, so what it says is whichever, as the name suggests, if this multiplicity is maximum, that is stable, and that will be the configuration. Okay, now let us consider this case, right, just to explain you. This is the PS. So this is what is happening, but let us say it will happen this way. This is the preferred one. It should be singly occupied, then pairing will start. But let us understand it in terms of this. So what will be the value of multiplicity here? It is 2s plus 1. What is the sum here? Plus half minus half plus half. So it is 2 into half plus 1, which is equal to 2. What is the multiplicity here? What will be the value? Half, 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 which is 3 by 2 plus 1, which is 4. So this is having more multiplicity. That means this is more favor. Okay, so unless they ask you talk about multiplicity, you don't have to really understand it this way. You just have to remember that electron starts filling according to Aufbau's principle, and once they enter a degenerate orbital, first all the orbitals will be singly occupied, then pairing will happen, and this is the explanation. All right, yes. Now, one big question is, why do they have different energies? This is what we understood with that arrow diagram and all that. I will give that complete list in a while, but you know it already. Why is there is difference in the energy? There is difference in the energy because of the shielding effect of the outer electrons from the nucleus by the inner electrons, which means the net positive charge by outer electrons is lesser, and that is something what we call as the effective charge. Alright, so look at that. If you are talking about I will tell you why the energy in this case is lesser. Let me just compare these two. Okay, so you have 2s and you have 2p here. Why is the energy for 2? Let me maybe consider 2s and 3d or something. Okay, so I'm just comparing these two. I know that 2p is lesser than 3d, but we are trying to understand why there is a difference in energy in the case of orbitals or subshells rather. Let us try to understand that. Okay, so now 2p is less than 3d is what we know. So in the third shell, there are some electrons, and here also you have some electrons, right? Now what is happening here is for the d orbital, there is shielding effect. What is this? The inner electrons, they act like a shield. See, the nucleus is trying to pull the electrons, correct? But these electrons, inner electrons are coming in between. So it's like I'm trying to pull you, but there is somebody in between who's stopping me from pulling you, kind of interfering with my pull, correct? Because of which my strength is kind of becoming weaker, right? So the same thing is happening here. The nucleus is not able to pull the electrons with the same extent because now there are some inner electrons which are obstructing, because of which the overall charge reduces, and that is what we call as the effective nuclear charge. It is lesser than the actual charge, okay, because of the shielding effect. The shield, the inner electrons act like a shield and prevents, or not really prevents it, reduces the extent of attraction by the nucleus of the towards the outermost electron, right? So that's the reason there is difference in the energy levels. All right, now having understood this, this is all you need to know. Having understood this, we will write the electronic configuration for most of the atoms. Up to 30 is what we need to know. Okay, but now you might be thinking it's a lot. It's actually easy. There are some exceptions which you need to know, but otherwise it is all good. Okay, so let us start with that. The electronic configuration. Let's start with hydrogen. In the increasing order of the atomic number I'm discussing, hydrogen has one electron, atomic number is 1. So where it will fill? 1s. In the 1s orbital it will fill. So what will be its configuration? 1s, 1 is the name of the shell, k shell, s subshell, s orbital and 1 electron. Okay, this is it. Now for helium, atomic number is 2. So each orbital can hold 2 electrons. In the 1s subshell, we have 1s orbital which can hold 2 electrons. One with a positive, that is clockwise spin, and anti-clockwise spin. So the configuration is 1s2. Whatever we write on top, that will be the number of electrons. Third one is lithium, it is 3. So here it is 1s, and the next electron, the third electron, which is the next energy level after 1s, if you remember that arrow mark, it is 2s. So it will come to the 2s1. So it is 1s2, 2 electrons in the 1s orbital and 1 electron in the 2s orbital. After that it is beryllium, which is 4. So it will be something like this. So it is 1s2 and 2s2. Correct? Now if you actually see this, this is what you have been doing. Correct? So I told you in your lower grades, if you tell you beryllium's configuration, you used to write 2, 2. You used to write like this. 2 electrons in the K shell, 2 electrons in the L shell. The same thing we are doing here. In the K shell there are 2 electrons, in the M shell there are 2 electrons. But we are writing in terms of exactly which subshell and which orbital the electrons are. We are going a little more deeper here. Boron is 5, so it will be, now look at that. This is 1s, both are filled. This is 2s, both are filled because 5 electrons. The fifth electron will come to the 2p shell. You don't, each one of this is px, py, pz. Okay, I cannot say first will go to px, it doesn't matter. So, but it will go to one of the orbitals. So, how you write it? 1s2, 2s2, 2p1. Okay, now if they ask you electronic configuration, you don't have to show this diagram. You just have to write this. I am writing this so that you understand it. Okay, now next is carbon 6. So this is same, this is same. Okay, so 6 electrons, 2 here, 2 here, and in 2p, one electron will go here, the 6th electron will be here because Hund's rule. Singly occupied pairing will not happen. So it is 1s2, 2s2 and 2p2. Okay, next is nitrogen, which is 7. This is same, and in 2p it will be 1, 1 and 1. Now it is singly occupied. 1s2, 2s2, 2p3. Count the number 5, 3 plus 2, 5, 5 plus 2, 7. That's how it. The first 2 electrons in the first shell in the s orbital, the next 2 electrons in the second shell's s orbital, and the next 3 electrons in the second shell's p orbital. That's what it means. Oxygen is 8. This is same. Now look at that. What is happening in the 2p shell? There were 3 electrons which are already paired. The 3 electrons which are already occupied. 4th electron will have to pair now. Okay, so this is 2p4. How we used to write 2, 6. Correct? 2 electrons in the first shell, 4 electrons in the second shell. Okay, so next after oxygen it is fluorine, which is 9, and neon, which is 10. So this part will be the same. Okay, so here 1, 2, 3, okay, 1 and 2. So it is, this part will be same, only 2p5 it will be, and here it will be 2p6. That means it is completely filled here. And that's the reason why neon is stable, because all the orbitals are completely filled. Okay, so that's about till neon. Let's continue and try to do it. Now, once you write neon, you can, every time, now if they ask you in the exam, I would say you write from the beginning. But now, when you talk about, I will write the names of everything once. Sodium is 11, magnesium is 12, aluminium is 13, silicon is 14, phosphorus is 15, sulfur is 16, chlorine is 17, argon is 18, then potassium is 19 and calcium is 20. Okay, now once you write, what will be its configuration? 1s2, 2s2, 2p6, 2, 2, 4, 6, 10, and next after 2p6 in the diagram, the next is 3s, so 3s1. Okay, so I will just draw the orbital for this. This is 1s, this is 2s, this is 2p, it's completely filled, and 3s there will be 1 electron. Okay, now every time instead of writing this, I can also write this much is the configuration of neon. So I can also write neon and 3s2. Neon is 10. That means 1s2, 2s2, 2p6 is already filled. That is neons plus 3s2. It is the same. So this is how you write. Okay, 2 electrons in the 3s. Now from aluminium onwards, it is neon, okay, which is 1s2, 2s2, 2p6, 3s2, and then it will be 3p1 here. Okay, and here it will be again the same, but 3p2, 3p3, okay, 3p4, because p subshell has got 3 orbitals, so 3 into 2 6, right? So up to 3p6 it is possible. 3p5 and 3p6 for argon. Okay, so all of them look same, just that here you will be writing for this aluminium you will be writing 3s, and then in 3p there is 1 electron like this. Okay, and this is same. How will you write? 1 here and 1 here, and here 1 here, 1 here, and 1 here for 3p3. For 3p4 all these are same. Okay, so I'm not writing it. For this it will be pairing will start now, correct? 4 will be here. For 5, 1 2 3 4 and 5, and for 6 it is 1 2 3 4 5 and 6. Okay, now let's talk about it. For this, look at that. It is again neon, which is 2p6. Always when you write, you cannot write for any element. Like I cannot write for chlorine and sulfur and all that. I have to write only for the complete octet. This is complete octet, right? So this bracket thing I can only write for noble gases. Okay, now once argon is complete, instead of saying neon, I can also say argon. So this has a configuration of argon, that is 1s2, 2s2, 2p6, 3s2, 3p6. Okay, so up to 3p6. The next will come to 4s. Look at that diagram. You had 1s, 2s, 2p, 3s, 3p, and then it was 4s. After that it was 3d. Correct? So it goes to 4s. So this is there. In the 4s you will have 1 electron, and for calcium it is argon and 4s2. Okay, now what I want you to note here is, look at that. You last year, if you remember, for argon you used to write 2 8 8, right? 18 electrons, 2 in the K shell, 8 in the L shell, and 8 in the M shell. For potassium, though the third shell is capable of holding 18 electrons, yet you used to write it this way. This is 2n square, 2 electrons, 8 electrons, 18 electrons, 32 electrons. But if it is able to hold 18, why do you write as 8 here? The reason now you are understanding, because once the 3p 8 electrons are filled here, the 9th electron is not going into the 3d. If it had gone into 3d, it would have become 9. But 3d is having greater energy than 4s. So since 4s is filled, that means 2 in the K shell, 8 in the L shell, 8 in the M shell, and 1 will be in the N shell. That's the reason. Now we are understanding it. Alright, yes. So that's it. Alright, so yes, I have done till calcium. We have to do another 10 elements up to atomic number 30, that is zinc, all the way from scandium, vanadium to zinc. We will continue that tomorrow. After that we will talk about there is some difference in the configuration of chromium and copper. It is little different from the expected configuration. We will discuss that. And the last topic is about the curves. And once we are done with the curves, that's it. So one more session and we are done with this topic. Yes. Alright. Bye bye for now.